Can you hear me? Hello? Can you
Yes,
hear
sir.
me?
Yes,
Yes.
sir.
Hello?
Yes, sir. Yes, sir.
Can you hear me?
Yes, sir.
Oh. Can you hear me? Hello?
Yes, sir.
Okay. Is screen visible?
Yes, sir.
Okay. Okay. Let me tell you that what I have taught. So first have a list of that. So I have taught first countable space. Second countable space. Separable space. To Nate. Okay. Separation axioms basically I taught only T1 and T2. T2 means house draw. I taught product and quotient topology. Now I want to, there are more important separation axioms. Okay, so that I want to teach you that. That means completely regular and normal. Okay, there is something regular also, but I may give definition. I won't teach much, but these two are important. So this is part of this, the higher separation axioms. Okay, so let me start with T1 and T2 again. Okay, so that here I am giving this first theorem from Willard, that theorem result. The following are equivalent for a topological space X star A. I'm saying every singleton, that is 1.68, it's got a name singleton, is closed in X star B. Okay. Every 1.68 is closed, and this thing, that for each X belongs to X, this singleton is the intersection of that U, such that U belongs to NX. Here I take, but you can take, but you take all the open neighborhoods of X. This is the family. I have taken neighborhoods to be open. I'm mentioning it. All open neighborhoods of X. So these two are equivalent. Okay, usually I have taken this as definition of T1. Some people take this, but here is another thing that is not mentioned here. Look, what is that? Given a pair of points, usually some people define by using C. Given any pair of given any pair of distinct points x, y, in X, there exists U belongs to NX, neighborhood of X, and V belongs to NY, such that this one X does not belong to V and Y does not belong to U. Look, I am not saying that we are disjoint. So this is weaker than house drop. I am saying you will get a two neighborhoods, one containing X, other one is the neighborhood of Y, such that neighborhood, of course, V will contain Y, but V won't contain X. There exists. And similarly, U is the neighborhood of X, so U will contain X, but U won't contain Y. I am not saying this. U and V may intersect. U and V may intersect. It is like this. Suppose you take this X, this is Y. Okay. Here you are taking a neighborhood of that. Okay. So let me see that X. X doesn't belong to V and Y doesn't belong to U, but they may intersect. Okay, so this is weaker than T2. That actually immediately tells that this is weaker than T2 house drum. Actually, some topologies they take it as definition, but usually we take it as this is definition, and it immediately follows. You should prove that. This is proof exercise. Okay, right? Okay, fine. This is T1. Now, look here. Fine. Suppose, so this is T1. Now you should prove this. We have seen that if you have a Hausdorff space, this is Hausdorff. That you usual definition that both analysts and topologists they take the same definition. Any two points, distinct point can be separated strongly. What is called strongly. This is separation is strongly, and previous separation is weak separation. That means given it is called Hausdorff. Given any pair of distinct points xy in X, there exist neighborhoods. You can write straight. Oh, sorry. There exist open sets U and V in X tau such that X belongs to U, Y belongs to V, and disjoint. Okay, it is called Hausdorff. This is called the strong separation. Strong separation. Because here you are getting the neighborhoods are disjoint. Previously it was weak separation. So that given any pair of distinct points, then it is called Hausdorff. So T2 implies T1. Okay. Now we see that there is some link with the first countable and between first countable and T1. Look, T2 I have seen that. In fact, for net I have seen that I will, but every convergent sequence has a unique limit. Every convergent sequence here has a unique limit. Question is that for T1 you do have it or not? Okay. For T1 we have this thing that you'll have to prove the result exercise. Suppose let X tau be a topological space such that every convergent sequence in X has a unique limit. Basically, X tau has a unique limit. Okay. Then X tau is T1. Is a T1 space. Is a T1 space. You can prove that every singleton is closed. So I'm leaving it an exercise. It's very simple. You don't need to ask, should not ask Sora. But converse may not be true. That you should find a counterexample. But the converse, that means T2, T1, in between this kind of space you have. Okay. Satisfying this property has a unique limit. Every convergent sequence has a unique limit, it is in between. So that it converts need not be true. So that you should find, but if you have first countable and T1, if you have first countable, okay. The question is that I say first countable plus T1. Does it imply T2? Okay, right? That you should think of. I'm saying the answer, you can find a counterexample. The answer is no. You can find a first countable T1 space which is not T2. Which is not T2. Because first countable space you can have only consider sequence. You need not consider net. Okay, so that every convergent sequence has a unique limit. Then X tau is a T1 space. Look at cofinite topology. It's a T1 space. That also has a unique limit because every sequence is convergent sequence is eventually constant. Okay, but that is not first countable. That is not first countable. Okay, so that here I'm giving you two exercises. This is also exercise. This is also exercise. But the converse need not be true. Okay, that means every convergent sequence has a unique limit. Converge, but sorry, you have a T1 space in which the convergent sequence has more than one limit. It did not have one limit. So this is exercise. I'm living with all this to you. Okay. Now T1 space. Now coming to T2 space. I will teach you something tougher things here so that students they understand it is not like Just listen to my lecture and it will help them. Okay. You need to act now. The house drop. Now look here. House drop, we have seen that X tau is house drop. If and only every convergent net has a unique limit. I have to give an alternative proof of this by using the product space. Now look, if you have X tau, then you can have the X cross X. It's called product topology. You take the product with itself, like you do in R square. Take the product with R itself. This is a topology. Remember here the base will be, this will be base U cross V. U V belongs to tau, is a base for the product topology. That it should work. Well, and another thing you should know that projections are also quotient map because this is open and continuous. So you have, this is called, some people write first projection. So it will write first projection. This is second projection. Pi 1, pi 2 are open and continuous, so that they are quotient maps. So they are quotient map also. Okay. Now, okay, you got it. So now in this, look, we talk about this X cross X. You can have this set T. Don't confuse with the directed set of that. I'm saying T, reserved is X, X. So this is called the diagonal, standard term, called the diagonal of X. Look, diagonal of X, but actually it's a subset of this. Don't confuse that T. Though we call it diagonal of X, but it's a subset of X cross X. Now I give this thing result. Okay, look, what is the result I am giving that? Let X tau be a topological space. The following are equivalent. Okay. X tau is Hausdorff, is T2. P. Okay. Every, this we have done, every convergent net in X tau has a unique limit. See, the diagonal, actually we should take this delta. This is the Greek D, big T. Greek alphabet, it is big T. So delta it should be. So you do not confuse with the diagonal of x. But this is a subset of x cross x. So this is closed in x cross x. It means with the product topology. In the product space, if we do not say anything, it has to be product topology. Okay, right? So look, A implies B, already you know the proofs. So I will prove B implies C at C implies A. So that I'm giving you the proof. Okay, proof B implies C. That we are assuming unique limit and that you'll have to show diagonal is closed. But again, you will use the concept of the net. So look, you take let xy belongs to this closure of triangle. This is the closure. It is not confusing. Closure of the diagonal in x cross x. Okay. So there exists a net. So there exists a net. Okay. X lambda, y lambda. This is the ordered pair. So this is another bracket in delta such that okay. Then look, you can actually YAN result is true component wise. Then x lambda converges to x. Sorry, I'm saying diagonal, so that y lambda has to be x lambda. Y lambda has to be x lambda. So this is foreign. So because this is in diagonal, so the element is this first entry, second entry will have to be same. But this will imply because x lambda goes to y. But this you can prove in YAN, that I'm going to tell you that. You just need a continuous functions in that. Okay. But that means what the look assumption in B, hypothesis is B is every convergent net has a unique limit. So the net is same. So by B, this is by B, x equal to y. That means you are getting, look, x is equal to y. That means xy equal to xx, which belongs to the diagonal. So this is closed. Hence, this is closed. This has been diagonal is closed. Okay. Now look here how to do that. Here, if you take this YAN result, I think I have done it. Let basically every continuous function like convergent sequence sends convergent net to convergent net. Here I are taking the first projection. First projection is continuous, so you will get this. Basically, you will be taking. Let me tell you. Okay, I will write that. Every continuous function sends convergent sequences to convergent sequence. Similarly, every continuous function sends convergent net to convergent net. Now look, this one, I take the projection, the first projection, pi 1, x lambda, this. First projection, this goes to this projection, that is x lambda. Okay. This, if you have this, then actually second bracket जरूरत नहीं है. If you understand. There is no confusion in that. Okay, but this is x lambda. So, okay, but you don't need bracket actually. X lambda, and this is x. So this is happening because the first projection is continuous. That is, remember, pi 1 is continuous. Similarly, since pi 2 is continuous, x lambda goes to y. Now you use that. You are having the same net going to x and going to y. By b, every convergent net has a unique limit, so x equal to y. That means actually xy is this, which belongs to the diagonal. Okay, right? That's it. Okay, that is C, B implies C. Okay, now C implies A. Well, the diagonal is closed. That is very important. Here you have the hypothesis is closed in x cross x product topology. To show x tau is Hausdorff. Here the proof is easier that it is Hausdorff if and only every convergent net has a unique limit. You are getting another third condition, diagonal is closed. Now look, here you'll have to show that any two points can be strongly separated by disjoint open sets. Okay, so take a point, two distinct points, x not equal to y. Since x not equal to y, xy doesn't belong to delta. Fine. Now delta is closed. It means what? But this is closed. This is your C in x cross x. That means there exists a neighborhood of this which won't intersect this. But that I can take basic neighborhood also. Because if a neighborhood doesn't intersect, that neighborhood contain a basic neighborhood that won't intersect. That means what I will get? There is a basic open set containing this. Not only an open set, basic open set containing which won't intersect this. So there exist, look what does it mean? That means there exist open sets U and V in X, because X cross X, such that XY belongs to U cross V. This is a basic open set. I am showing you because how to use the product topology, how to work with the product topology. And U cross V intersection to phi. Okay. Look, I have used this thing, doesn't belong there, and this is closed. So that since this is closed, that means it doesn't belong to the closure. That means there will exist an open set containing this point which will intersect this. So any open set that can be replaced by a basic open set. That I'm saying. Okay. Because any open set containing xy will contain an open set of this form. Okay. Now you look, xy belongs to U cross V, and my claim is that U intersection V is empty. Look, xy belongs to U cross V implies x belongs to U, y belongs to V, and I am claiming this. So that is obvious. Look, if you have a point xy belongs to this, look, suppose this is belongs to this, not this same xy. Take x prime, y prime. Okay, sorry, wait a minute. Let suppose you have a point that it is not, suppose not, then let x prime belongs to U intersection V. Suppose, okay. Then you look x prime belongs to U cross V, because x prime belongs to U as well as V, but this belongs to here also. That means this belongs to this intersection, which is disjoint. So it is not possible. That's the proof. Okay. So it is Hausdorff. So remember that here Hausdorff we are linking with, this is diagonal is closed. Okay. Fine. Now let's see. Well, so this is Hausdorff. This I have done. Now the next thing is that result. I am doing it. That you can, that I have said, every subspace of a Hausdorff space. I think I have given an exercise. Hausdorff space is Hausdorff. P. If tau y is a family of Hausdorff spaces, 52 spaces, then the product space. When we don't say that, it means the product topology. And this is, you can write product topology is also a T2 space. C here, that is the quotient. Quotients of T2 space need not be T2. For quotient space, you need to be careful. So here exercise I am giving. Find the counter example. Okay. Right. Fine. This is a counter example. You should think about it. That in fact, Ali Francis has given this one thing. He has given example for Ali Francis Berkshire for different thing, but that example should work. Okay. That why quotient of a Hausdorff should not be Hausdorff. Okay. First of all, they should have something non-Hausdorff space. Then you think that how will be a quotient space of another Hausdorff space. Okay. Now the thing is that, okay, result I'm giving this. Suppose this. I'm just saying, but I have done this. Let x tau, sorry, f1, f2, fe, oh, fe, x tau, y sigma be a continuous map and y sigma be a Hausdorff space. Then take this point A, Look, this is in x cross x such that fx1 equal to fx2. Look, I am not using xy because it's a convention here. Y is here. So if I take y, it is understood it will be from the range, but it is not from the range. It is from the domain. So that's how I'm using x1, x2. So x1, x2, you are taking x cross x as that this. So the product space is closed in there. Okay, right, is closed. Well, net will be good enough than that because this is given continuous map. So look, if you take x, can take x z belongs to a bar. Okay, so there implies there exists a net. Net you should be careful about. But how do you take that? Okay, well, I think it will be a bit confusing. Let me see that. How to do that? What is doing that? Okay. Well, I think go straight. What I will do that, if a point doesn't belong here, it cannot be a closure point. So take a point x1, x2, suppose doesn't belong to A. If doesn't belong to A means what? Fx1 equal to fx2. So that fx1 not equal to fx2. Here I am using house drop. Since y sigma is house drop, these are the points of house drop. Since y sigma is house drop, there exist open sets v1, v2 in y, that is y sigma, such that fx1 belongs to v1, fx2 belongs to v2, and v1, v2 disjoint. Okay, disjoint. Well, now look, x1 belongs to f inverse v1, x2 belongs to f inverse v2. Look, v1 is open, so that this is open in x because f is continuous. Similarly, this is open in x. Okay, right? Open in x. So that means what you are getting? That means x1, x2 belongs to this open set. This is a basic open set actually in the product space. Okay, right? And the product space. What I need to show that this A is closed. Basically, I want to show that I am showing it that a point outside A cannot be a closure point of A. So that means I will show its intersection with A is disjoint. Because of this, it will happen. Look, I want to show that. Look, F inverse. Sorry, not F inverse V1 cross F inverse V2. This intersection A is disjoint. You'll have to show that. Okay. Remember, A is this. fixture. But here I have taken a particular point. Don't confuse with that. Here I have taken a point x1, x2 doesn't belong to it. So this is a giant thing. So don't confuse with that. Okay. Well, if you take a point here, take z1, z2. You can call it, otherwise you will confuse that. Right. Suppose you have z1, z2 belongs here in that intersection. z1, z2 belongs to A, implies f z1 equal to f z2. Okay. On the other hand, z1, z2 belongs here in this implies z1 belongs to f inverse v1, z2 belongs to f inverse v2, implies fz1 belongs to v1, fz2 belongs to v2. But this you have, that means v1 intersection v2 not disjoint. But previously that's the way we chosen. That if v1 intersection v2 is, look here. Here. This is Hausdorff. You need Hausdorff, okay, for your proof. So this is closed, okay, right? Well, next result is saying you are playing with Hausdorffness. How Hausdorff is important. Okay. The next result is, now look. It is basically converts of sort of converts of the previous result. That means let f is an open map. This x tau let sigma n onto open map and this previous set and A is closed in x cross x, then y is Hausdorff. Look here, I'm assuming this is open. Okay, right. Open and this, okay, right. Then y sigma is Hausdorff. That's what I'm saying. That how he is proving in that. Okay. Look, here you take two distinct points. How to do that? It is very simple, straightforward. But look, this is onto. So there exists x1, x2 in x such that y1 equal to fx1, y2 equal to fx2. Now see that y1 not equal to y2, so fx1 not equal to fx2 implies well, got it. But this doesn't mean this is doesn't belong here because A is this. That means x1, x2 belongs to x cross x minus A. Okay. Right? Fine. Now look what I'll do, how I'll use product topology. I'm basically teaching something about product topologies, how to use them. Look, A is closed there. So this is open in the product topology. Right? But product topology, this is open. How do I handle it? This is an open set containing in that. That means I'll have to go for basic open set. So there exists open sets UV in X such that I have this. Got it? Now look, what does it mean? Look, first of all, you should figure out that U cross V is outside A. That means for the points in U cross V, you do not have this. That means you do not have equal to this. Okay, right? So that what will happen? Look, I need to show this is house draw. Okay, right? And where I have not used this. So I will have U is open next. So FU is open. F is open. I need to show. Now look, x1, x2 belongs to E cross V implies x1 belongs to U, x2 belongs to V implies fx1 belongs to fu, fx2 belongs to fv. But f is open. This is open because f is an open map. This is open. All I need to show that, look, fx1 was y1, fx2 y2. So all I need to show that I think this you can do. Then I'm done. Then y sigma is house draw. So I'm leaving it to you. That you can everything you have here. You need only 2 lines. Okay, do that. Okay. Look, if you have a point common here, you should know that what will happen. Okay. If you have a point here, it implies there exists. Don't take x1, x2. Z1 belongs to U such that y equal to fz1. Similarly, there exists Z2 belongs to V such that y equal to fz2. Y equal to fz1 equal to fz2. So that fz1 equal to fz2. That means Z1, Z2 belongs to A, right? But how Z1, Z2 came that? Look, remember that Z1, Z2 belongs to U cross V, which is contained in this. That means this is outside this A, and here you are getting inside this. So you are getting a contradiction. Okay, right? Fine. That I have done the proven the retract on that. Okay, so you do as many as house drop on that. I am just showing it. That how you use product topology definition. Product topology, you'll have to go through the basic open set. That much information we have it. Okay. Now, look, in T1 and T2, I'm just giving an introduction. Tomorrow I'll teach you that. We are doing separation by open sets. But what about separation by continuous function. Let me tell you that. What do I mean by continuous function? What does it mean? That because in analysis also we actually bank more on this separation by continuous function. Here you look this. Suppose we have a function, continuous function. Suppose you have it with the usual topology. Suppose you have a continuous function. And suppose fx equal to some point, sorry, x1, x2. Take a point here. Suppose fx1 equal to 0 and fx2 equal to 1. Suppose you have it. Then what it implies? Now look, that x1 belongs to, f inverse look, this is open here, though it is subspace topology, it is open here, and x2 belongs to f inverse 2/3 1. This is also open here. So this is, call it U, call it phi. Now look. Look, U and V are disjoint because values in U is going to be the less than 1/3 and here greater than 2/3. So obviously it will be disjoint. So that means if you have such a function, basically it is separation by continuous function, 2 points. Here it is 0, it is 1. Then they will be separated by a disjoint open set. So this is basically stronger condition. And when separation by continuous function. Separation by continuous functions, initial will be like this. 4 points. Definition. Let x tau be a topological space. Two distinct points x1, x2 are said to be separated by a continuous function. If there exists a continuous function f x tau, the usual topology, such that fx1 equal to 1, 0 and fx2 equal to 1. But there is no preference between 0 and 1. Look, if you have this continuous function, so this is your continuous function. Here I am taking a function where y is going to 1 minus y. So that will interchange. So if you take g dot f x1 will be g fx1. That means g0, which will be 1. Similarly, g dot f x2 will be 0. So that there is no preference that whether which one will take 0, which one will take 1. Okay, right? And also you can see that if you have separation by a function, there is no preference about that. I could take any closed interval because they are homeomorphic. If you have it, you can have another continuous function like this. You take composition, and if you have this, go other way. You take a composition. That will get. So that there is no preference here. Any closed bounded interval will work. Okay. So suppose you have such a function. Okay. I will talk about more about this, but I am giving an exercise here. What is exercise here? Exercise this. Let X tau be a topological space such that any two distinct points, of X can be separated by a continuous function. Then it's not the same function, depending on the points, pair of points, which is any two distinct pair can be separated by a continuous function. So that was actually proof was included in my discussion. So that X tau is Hausdorff, but this condition will be stronger than Hausdorff. Can you find an example of a topological space Hausdorff Hausdorff space such that there exists a pair of points, Hausdorff space X, there exists a pair of distinct points in X which cannot be separated, which can't be separated by a continuous function. Think about it. I think you understood that. If you want to understand point set topology, what I am teaching in this course, you need to understand the analysis well also. Here I am bringing analysis. So think about it. Okay. So I will teach you tomorrow. Okay. Fine. See you. So tomorrow basically I will start completely regular. Before that I may give you something brief introduction to regular space, but I won't use regular space. I will use complete regular and normal. Okay. See you. Tomorrow I will take the class as usual. Okay, bye. Hello, you can hear me? Hello?
Yes, sir.
Yes,
Okay,
sir.
tomorrow I will take the class. Okay, fine. Now think about the counter
Okay,
examples
sir.
I have given on that. We work with the Hausdorff and the product topology. Whatever theorem I taught, result I taught, make sure you have a look at that. I will give similar things in the exam. Okay, bye.
Thank you, sir. Hello, Deepika.